2022. Our project is on the redesign of the suspension and hub assembly for optimization. My name is Pelaez. My teammates is Rojas and Diaz. So we have the purpose of our project is to redesign the suspension package that was to be a participant in the SAE competition. Our motivation and goals is to rank top 50 in the competition. Since last year we didn't make it that far. We want to complete all the dynamics events, and we also want to eliminate all the failure modes that we had in the suspension last year. Part of the suspension that we work on is the suspension is composed of a double arm suspension with a push and pull rod setup. We made it out of steel tubing. Initially, we were thinking about making it out of carbon fiber tubes. We're still researching about it. We did make some prototypes, but our final design was made out of steel tubing. The brakes, also part of the suspension, they provide force to stop the car, and they also add forces to the suspension. Mostly of those forces are going to be torsion to the A-arms. Next component are the uprights. The uprights are very important component since it attaches all the parts together. It holds the wheel, the brake rotor, the brake caliper, holds the A-arms, so it connects everything to the chassis. So basically it transfers all the forces. To do our engineering analysis, we looked at our competitors. We compared, the top-ranking cars with ours to redesign. We also analyzed the forces that we're going to be experiencing to design a high-performance suspension. So here we have some diagrams of the suspension. First, we started with the wheel. We have the friction force, lateral force coming from curve. In the case going in a curve, the normal force in the tire comes from the same weight of the car or for bumps on the car. These forces are transferring to the A-arms. In this condition, normally the top A-arm will be in compression and the lower arm will be in tension, but it changes. It depends on this dynamic system. The forces will be in tension and compression, changing all the time. Here we have the geometry of the front suspension. You can see we have forces coming from the side, from the curve, and also the brake force. In the case of a braking force, it will be like 1/8 of the braking force since there is 8 arms in the car. Next, we have also taken into account the suspension forces. These forces add tension to the A-arms. And then we have here the lower image, the geometry of the rear suspension. Since this is the geometry, the force in the back member is amplified. We have the final equations that we came up with that take into account the braking forces, acceleration forces, suspension forces. Basically, the most important forces that we looked at is the rear, which you can see it multiplies the force by a factor of 1.7. Having all these equations, we came up with a calculator, forces calculator, with extreme conditions. When accelerating at 10 miles per second square, decelerating in a very, very sharp curve. These are the forces that are going to be experienced. This is what we work with to design the suspension. As you can see, the final forces on the front and on the lower and upper A-arm are in tension and compression on the reg. Next, we have all the forces in each member. What is important here is the biggest forces, which is about 2,000 pounds in tension and about 1,900 pounds in compression. So we designed for these forces, to make it good enough it doesn't break. Next, we did a dynamic analysis by knowing some of the constants that we have, like the spring constants. And knowing also that to get the best performance, we need to have a fast response suspension. We determined that the best ratio of damping is 1. This graph right here, we can see the damping ratios, which means the fastest it comes back to be into the rest position is the best. So as you can see, the blue line is the damping ratio of 1. Another calculator that we made, this one, it's to determine the damping constant that we need for the front and the back by knowing the weight of the car, knowing the spring constants, knowing also the tire spring rate. So we came up with a specific damping constant that we can tune into the suspension to make this damping ratio of 1.
All right, so now that all forces have been understood and are now known, we have to move on to the material selection of the car. Now, this is very important because there are several things that need to be taken into consideration when deciding the material. Specifically, how does this material perform in a finite element analysis? Also, how does it perform when it comes to cost and benefit? And then finally, what is the manufacturability of this material that you're working with? So specifically, the two main types of materials chosen that were used on the car were steel and aluminum. In some cases, we were forced to use aluminum due to its lightweight characteristics, whereas in other cases, we actually had to choose steel due to its easy weldability. And then finally, we end up moving towards the stress analysis now that the material of the parts have been determined. So specifically for our uprights, we had a factor of safety of 3.3. Now, keep in mind this is under ideal loading conditions, very normal. Now, we have 15,000 newtons placed at the upper and lower portions of the upright of the inner diameter, and roughly 950 newtons on each mounting point for the brake caliper. Next, this takes us to the wheel hubs. So in this case, we actually have 225 pounds of force, roughly, located at the front face of the wheel hub. We have normal forces from the spindle as well. And in this case, we actually have a factor of safety of 1.34. Now, why that factor of safety is something we'll touch on a little bit later. And then finally, the bell cranks. These bell cranks actually have roughly the same strength as last year's models. And last year's models featured basically a completely solid design, whereas these ones have had a significant amount of material. So the main benefit with this is reduced material, same strength, and can perform just as well. Now finally, this takes us to the manufacturing of all the parts. So for the uprights, being that they were a more complex part, we actually outsourced these to CMA Engineering. One of the main reasons that we did this outsourcing was because there's an extremely tight tolerance for the bearings that were to be press fit into them. Due to our manufacturing capabilities at FIU, we normally reserve the manufacturing for on-site parts for something that requires a little bit less precision. So next we move on to the A-arm links. You'll notice we actually don't have the picture of the A-arms because we wanted to really put emphasis on the fact that we actually have to create a jig in order to ensure that no variance is created when designing these A-arms. And also another thing to point out is that we designed these with a factor of safety of 1.2. Now this somewhat low factor of safety is of course under extreme conditions. However, it's meant to be somewhat of a fail-safe, much like a key in a gear. And then this, for the manufacturing, this takes us on to the cost analysis. So what you're seeing here is the cost of basically every part of the vehicle, coming to a grand total of $7,375. Now keep in mind, this is the theoretical cost in which no discount has been applied. But thanks to our sponsors, we ended up with a grand total cost of roughly $2,000. And the highlighted points you can see were either free or significantly reduced in cost. And the assembly of the car. There are two primary forms of assembly when it comes to this vehicle. First are your typical bolt and nut assembly, As per the FSAE regulations, all bolts used in the assembly are grade 8. And then finally we move on to welding. Careful attention must be paid to welding because since we are using TIG welding, there must be a lot more control and I guess you could say fluid movement when performing the operation.
I'd like to talk to you guys about the prototype design. Special attention to the hub, the spindle, upright, and the arms. Those were some key points that we'd like to point out and what we really focus on in this project. Here you can see an overall assembly of one of our earlier prototypes. You can see a lightweight hub, 2 roller bearings instead of 1 that we used in previous years, and a earlier prototype of the upright. For our rim and tire, we decided to stay with the same compound as the previous season. We did this to set a trend for following years. We want to get more data and analyze the amount of forces that we can attain with this and see if we are able to outgrow them or stay with them to maximize the amount of performance with the weight of our vehicle and our configuration. We also decided to change the rims this year. We went for a lightweight 3-piece just because of the amount of customizability that you can do with the internal ring. And it results in an overall decrease in non-sprung weight. Here you can see a difference in dead spindle to live spindle. This year we are running live spindles. The reason for it is we were able to fix some of the issues we had with the bearing loading within the upright, and it results in an overall more rigid upright as compared to the dead spindle design. Here you can see our wheel hubs manufactured. You can see that they're relatively small, around 4 to 5 inches in diameter, and they obviously use less material than the previous model, and we also outsource this machining. Here are our uprights. They were financed by the Toyota Technical Center. Doing so allowed us to receive their key inputs to our design, and as you can see, we are running our live spindle design with 2 internal roller bearings, just because of the amount of weight savings due to compared to a one bearing design or a dead spindle design. Our belt cranks, as Marco pointed out earlier, we outsourced this to a water jet company. Due to an increase in funding, we were able to decrease the amount of weight significantly, about 80%, while still maintaining the same amount of structural rigidity and factor safety. Some of the testing and evaluation that we do throughout this project, we'd like to point out 2 main factors: the strain per A-arm link, and the acceleration sustained through cornering and driving through a straight line. You can see in some of the pictures the 2 tests that determine this: the skid pad test on the upper right and on the bottom the acceleration test. For the A-arm forces, or the strain per A-arm link, we decided to use T rosette strain gauges. This allows us to see if there is any bending within the A-arm link. Obviously, bending within between a member that's in tension or compression is something undesirable. We decided to go with Vichy 125 UT, specifically because Vichy is a sponsor of FSC, and they have seen many cases where an actual strain gauge was not sufficient enough. We were able to get the force generated from the A-arms by using a simple strain equation made to find the force actual with the elasticity of material and the strain obtained and the cross-sectional area of the actual link. As for acceleration testing, you can see that it can be determined in several ways: either simple particle kinematics using timers and distance traveled, or accelerometers. In this case, we were able to purchase a Race Technology DL1 DAC. This comes with an inboard accelerometer, which allows us to obtain a friction circle, which displays in a neat, organized fashion how we are using our tires and how much G's are we obtaining throughout the event. As you can see here, we did some testing. Although it was kind of messy, the main circle in the middle towards the right, you can see that we gone in and outwards towards the circle. We did this to simulate the skid pad test. We didn't do 2 loops just because there wasn't sufficient amount of space. We would go counterclockwise 2 times and then clockwise twice. And the following image, or the following slide, you can see a video of the testing done earlier today. As you can see here, you start at the beginning, you start the vehicle, and then you start decelerating through the curve, maintaining as much of speed as possible, but while still maintaining the grip. Due to accelerometers within the DL1 data acquisition system, we were able to graph and plot any accelerations with respect to time. Here's data obtained from those testings. As you can see, you're able to see the lateral G's switch from negative to positive based on whether we're going counterclockwise or clockwise turn. The maximum G's achieved at these speeds and at this diameter, we were able to achieve a maximum of 1.24 G's. We calculated 1.19 G's, but it superseded our calculations apparently. For the next test, we decided to do acceleration and braking. Since it's a similar layout, we decided to do it both at the same time. The brake test considers a full lockable all four tires, and if you're able to do that, you simulate the maximum G's achieved during deceleration and acceleration. We'll see if you're not slipping on the tires, you achieve maximum acceleration. Here's a short video of that acceleration test and brake test. From those tests, we determined that a maximum longitudinal acceleration of 0.86 G's was achieved consistently, and a maximum longitudinal deceleration was achieved of 1.11 G's. This also superseded our calculations by at least 0.05 G's or more. As for evaluation, we decided to use the same equations used in competition for our scoring. We did this in order to almost place ourselves in the competition based on previous year's points and times gained done by different competitors and the rest of the 120 teams within the competition.
All right, for the design experience, the first thing I want to talk about is health and safety. So previously I was talking about one of the components and how it was featuring what seemed like somewhat of a low factor of safety. Now the reason why this was done is we had to find, being that this was a high performance racing vehicle, we had to find the fine balance between safety and reduction in weight. And for that particular part at roughly 1.2 for the factor of safety, that was our point of fine balance. And the intense engineering analysis had to be performed for every single part in order to maintain that balance of safety and weight reduction. And in addition, being that we were working in the machine shop, constant attention to PPE always had to be held. That just goes for any work environment. The two primary standards used throughout this project, well, first, being that this is a SAE sponsored event, many of the rules and regulations are held by the SAE. And then in addition, ASTM standards were used for all of our medals. So some lifelong learning experience that we've gained with this project. Time management would have had to been probably the most valuable thing we have learned. Being that this is a very fast-paced environment, SAE, we realized that being that many parts were outsourced and needed to be manufactured, all deadlines had to be taken very seriously. Another thing that was learned is task delegation. Yes, as mechanical engineers, we do have to focus on design work. However, we also have to be project managers at the same time. And in order to work most efficiently, we had to delegate several tasks to other team members, also new team members as well, which helped transfer the learning. GD&T was a major learning point for us. At that point, we realized you really must pay significant attention to tolerancing whenever sending outsourced parts to another manufacturing site. Global responsibility. Although one may not think of a suspension as something used to help the environment, we did a lot of research on carbon fiber components. Now, the reason why we did this is that we believe that by doing more research in carbon fiber components, that knowledge could even be applied to other structural components within the vehicle. And thus, that additional weight savings could possibly lead to a reduction in fuel consumption for a vehicle. Here's just a little bit of a timeline of the progress for this particular project. And in conclusion, not counting the wheel and tire combination, we managed to reduce the weight of the entire suspension package by roughly 36%. In addition, we also increased the strength of all of the arms within the vehicle while reducing the material used. And then in addition, we successfully managed to validate our data by performing a skid test as well as a brake test. We would like to thank all of our sponsors. Also, we would like to thank Professor Ziccarelli, who's sitting in the back, for a lot of help and advice with the manufacturing of our components. Finally, here's a picture of the finished vehicle. And then after that, we just have a brief slideshow of some of the parts and components of this vehicle. And during that time, we welcome any questions.
Did you have any issues on tolerancing on parts that you outsourced?
Yes, we did have a couple of issues.
And how did you handle it?
Most of the time they were plus or minus 5,000s, 10,000s tolerances, so we were able to use different spacers and different bushings in order to fix those tolerances.
Were there tolerances